Okay, here we go. 6-9, number 4. There's a flagpole. There's a ball on the end of the flagpole. The flagpole is a length L at an angle theta initially. And then the golden ball at the top of the flagpole decides it's going to wiggle loose and fall. So, and the question then is, what is the angular momentum of the falling ball with respect to the bottom of the flagpole here? So, this is another one of those weird ones where something moving in a straight line does have angular momentum. That angular momentum is changing over time. It's just like we saw in the projectile motion problem. So R cross linear momentum is your angular momentum. Since the ball is falling vertically, the linear momentum is vertical the whole time and increasing. So we have an increasing linear momentum, which probably means our angular momentum will also increase. But also we got to do the cross product thing. So we're using the position vector and crossing it with the angular momentum vector. So we need the perpendicular component, so we need the horizontal component. So even though the stick is changing its position the whole time, or not the stick, the position is changing the whole time and moving through an angle, the horizontal component is remaining the same. So that's our L cosine theta component. Doesn't matter if the ball's here, that still has the same horizontal component, or the ball's down here, it still has the same horizontal component relative to the base of the flagpole. So that's our L cosine theta. That's going to be our position that's always perpendicular to our linear momentum. And then the linear momentum is increasing because gravity. So let's see. That basically sums it up, right? And they want it as a function of time. So the velocity at any point in time is just gt, right? It's accelerating. There's no initial velocity, 0. Only thing accelerating is gravity, so 9.8 times t is going to be your final velocity for any of the positions. So there you go. L cosine theta is perpendicular to the linear momentum, and then we're going to find that by doing mgt as a function of time. It is a little tricky when you put this thing in WebAssign because they are kind of particular. They want you to have to think about that right-hand rule thing. So then in the last step, I'm going to throw in a negative sign because my right-hand rule, right, position, crossing into the direction of rotation around the pivot point, which is the base. So that thing is kind of technically rotating in that direction. Or I can pick any one position and say R, velocity, boom, into the board. So if it's into the board, the WebAssign defined out of the board to be positive. So into the board is negative, boom, negative. And it's the into and out of the board direction which WebAssign defined as the K direction. So we got to add in your negative and then your K hat using the little trig symbols. Part B just asks, what is the torque causing the change in angular momentum? It's gravity. Mg is pulling down. Very similar. Its torque is also changing as this position vector changes as well, right? Because torque follows the same rule. It's position cross force. So the force is mg. The position then is still L cosine theta. So the torque is changing, which is causing the change in angular momentum, just like by definition, right? Angular momentum remains constant unless there's an external net torque. So we've got an external net torque from gravity that's varying as it falls. So the angular momentum varies. However, in part C, it wants you to know the rate at which it's changing because it is changing at a constant rate. Dependent on angle though, right? So all we're doing then is taking the derivative with respect to time, which is just L cosine theta mg. So that one's pretty easy, part C. Again, a weird one with straight things having angular momentum.